Welcome to the Wing Wag. I'm your host, Jack O'Lind. I'm an instrument-rated pilot and the owner of an aviation company and flight school here in Central Florida.
This podcast is for informational purposes only and is not guaranteed to be accurate or complete. While we research each topic, we are humans and occasionally make mistakes. For the most up-to-date information on regulations, check out the official Federal Aviation Regulations, also known as the FARs, or consult an aviation attorney. Lastly, the opinions expressed on this podcast are the guest's opinions and are not necessarily the opinions of the host or podcast. Welcome to this week's episode of the Wing Wag. In the previous two episodes, we talked about some of the more primitive forms of navigation, dead reckoning, and celestial navigation. And in both of those episodes, I mentioned how navigation is kind of at the forefront of human technology at any given moment in time because of how important commerce is and also like the military applications of navigation. So the current state-of-the-art navigation technique is kind of always like at the forefront of the technology of the day. And you have some of the cleverest minds of the time working on problems that are related to navigation. But this week's topic, radio navigation, is a little bit different, where it goes from just using kind of human creativity in the way that you observe yourself and your state and the universe to kind of a harnessing of physics, right? We take something that is just naturally occurring, electromagnetic radiation, like visible light, radio waves. We think of radio waves as man-made because so many of them are now, but they are just a naturally occurring phenomenon. Like a lightning bolt creates radio waves. The sun is constantly releasing radio waves. We have the cosmic microwave background, which is just kind of an electromagnetic wave that's coming from everywhere in space at all times as a remnant of the Big Bang. But sometime after World War II, we or a little bit before World War II, we were able to harness these waves and use them create them in a predictable way and use them in a predictable way to effectively transmit information over large distances and indirectly use that for navigation. Let's get into it. Like I said, I mentioned World War II because radio navigation got big during World War II and after. Even though it had been around a little bit longer since probably the invention of the radio, they'd been thinking about this like sometime back in the 1800s. But we can think about like what happened right around World War II that necessitated a complete change in the way we had been navigating. And that's basically the advent of airplanes being used very frequently for military purposes, right? So while planes were invented a little bit before World War I, and they were used in World War I, they really saw an uptick in military use in World War II. Because the planes that were built during the time were a lot more capable than the flimsier looking fabric biplanes of World War I. They were capable of flying a lot longer distances over vast expanses of water. They were capable of flying at night and flying a lot faster than the old airplanes. And this necessitated a new form of navigation that was a little bit more, I don't want to say robust than celestial navigation, because celestial navigation is in a way like the most robust, but the most reliable in the biggest variety of situations, right? You need something that you can do at night, during the day, in bad weather, when you're outside of the visible distance of land. You need something that you can do fast, right? If you're flying alone in an airplane at night, maybe you don't have time to sit there, pilot the plane, and work a sextant to figure out your rough location. You need to know what your location is pretty accurately and right now. And also, this airplanes were beginning to do instrument approaches, where anyone who has their IFR, their instrument rating, will know about this. An instrument approach is it's a procedure that you follow that brings you into an airport and lines you up with the runway, and it has a certain minimum. So the approach will bring you down to that minimum altitude without you having to see anything. And then you need to be able to see the runway at that minimum altitude, and then you take over and land. But it guarantees that you'll be clear of obstacles. It guarantees that you'll be on a safe glide slope for the runway. And at this time, like, the US was creating more instrument approaches for airliners, for military uses. And at the time, basically, radio navigation was going to be the only way to achieve this. Celestial navigation just did not provide the speed needed to get these readings, like, continuously, and it doesn't work in fog. Obviously, you can't get a reading on anything if it's foggy, and it needs to be very accurate. And one little note that I will say is that technically, GPS is radio navigation, right? The GPS waves that are sent out from the satellites out in space, the GPS satellites, are a form of electromagnetic radiation, and the receiver on board uses the signals to calculate the location. So it is technically a portion of radio navigation, but we're gonna cut this out and make it its own episode in the future, so we can focus on kind of the traditional methods of radio navigation, from RDF up through, like, VOR, DME, LORAN. I guess we can differentiate it kind of like ground-based radio navigation versus space-based radio navigation. We're going to focus on the ground-based radio navigation. So as the name suggests, ground-based radio navigation requires something on the ground emitting or receiving a signal that the receiver in the airplane can somehow interact with to judge some information about your position. Maybe you can use it to find your bearing. So kind of like what direction you'd have to fly to get to the station, where you are relative to the station radially, your distance to the station, for example. In the first method of radio navigation, at least the first that I found that seemed to be kind of widely used in aviation, was called RDF, or radio direction finding. Let me actually quickly verify that is what it stood for before I just spout it out. Yep, RDF, radio direction finding. And so this relies on a physical principle called Faraday's law. We won't get into too much of the physics here, mostly because I don't understand all of the physics here. But the basic idea is this. You have an antenna, a beacon. In this podcast, I'm going to refer to transmitters as beacons. So you have a beacon somewhere on land, and it is broadcasting a signal just everywhere. It's in all directions. It doesn't matter what the signal is. And then on my end, I have a loop antenna. So it's like a metal loop that goes down like this. And Faraday's principle says that the strength of the signal that you receive through this loop wire is proportional to the rate of change of the magnetic field going through the loop. And the way that electromagnetic waves are shaped, the only time you have the magnetic field actually going through the loop is when the loop is facing edge on to the beacon. In other words, like, the circle is not facing the beacon. I can't see the beacon through the circle, right? And so if I have the antenna edge on to the beacon, I should be able to receive that signal. But then as I rotate the loop antenna so that slowly it's like opening up towards the beacon so I can see it through, the signal should get weaker and weaker until we hit no signal at all when you're directly facing the beacon. And we call that the null. And so using that, you can deduce where the station is, like, even if you're blindfolded, right? And there's a really good Veritasium video about Amelia Earhart's flight, and he goes into exactly how to use the loop antenna blindfolded. But you can find exactly where you need to go to the station. And if you know the location of the station, you have an idea of where you are, right? You don't know your distance to the station yet, but we know which direction we have to go to get to it, right? So if we can do this on several stations, we can plot these lines on a map, meaning like, okay, I know I'm 90 degrees of this station. I don't know my distance, so I might be anywhere along this line. Likewise, I know I'm, 120 degrees from this station, and I don't know the distance, so I could be anywhere on this line. So I plot both of these lines, called lines of position, on my map. Where they intersect, that must be my location. So this was a really breakthrough idea. And I love the simplicity of it. It requires, like, the ground station just has to be any antenna. Like, it doesn't have to have any specialized hardware. It's just an antenna that broadcasts. So if you know the location of any transmitter, you could use this method to navigate based off of it. You can use an AM radio station. You could set one up at your house. Maybe, I don't know the legality there. But in principle, you could set one up at your house. The only downside to this is that it does require you to mount this loop antenna on your airplane and then operate it kind of manually to find the null spot, right? And additionally, I had read somewhere that the bigger the loop is, the more like clearly defined that null position is. So the better accuracy you get in finding your bearing to the station. But that presents a problem. If you have a very small airplane, you can't mount just this giant loop on it. So the next iteration was a pretty obvious one. It was kind of reverse the roles of the receiver and the transmitter. Instead of having the transmitter be a beacon that just broadcasts in all directions and having the receiver be this rotating loop antenna, let's switch it. Why don't we have the transmitter be the rotating loop and then just have a single normal antenna on the receiver, on the airplane? And the idea, you'd have to add a little bit more to it. So the basic idea here is the transmitter, the beacon, is this spinning loop and it's broadcasting. But whenever the loop is facing the airplane exactly, kind of the inverse of the situation when we had the loop on the airplane, when the loop in the tower is facing the airplane exactly, we should pick up no signal. We should be in a null, right? This doesn't exactly tell us where we are with regard to the station because we don't know, or we haven't assumed that we know the rotation speed of the loop in the beacon, and we haven't assumed that we know where, like how the beacon will be rotated at a given moment in time. So to get around this, what they did was they made it so that every time the loop passed through north, it would broadcast a unique identifier on a normal antenna in all directions. And so the airplane could pick up that unique identifier, and then we would know, okay, we must be listening to this beacon. And then a little bit later, you'd have the null from the loop antenna. So by measuring the time between hearing that identifier and receiving the null from the antenna, and these towers would publish their rotation rates. So that was actually known. The rotation rate was known. And by calculating that time between the two measurements, we can know exactly where we are with reference to the tower, to the beacon. And so this provided a number of advantages over the previous RDF system. The biggest one being its higher accuracy, like I said, because we can have a bigger loop antenna in the beacon than we could have on the airplane. Plus, like the loop antenna in the airplane was like hand operated, so people weren't getting like the best of readings, whereas with the tower, it was a little bit more automated. And But this does add complexity to the beacon, right? They're a lot more expensive to set up because it's now not solely just a single normal antenna broadcasting in all directions. It's that plus this rotating antenna, plus you have to make sure that it's spinning exactly at the published rotation rate, plus you have to make sure that the normal antenna broadcasts the identifier only when the loop antenna is pointing north. So there's a lot of moving parts here, and more maintenance, more upfront costs. This system is called reverse RDF for obvious reasons, right? RDF, radio direction finding, was when you have the loop on the airplane. Reverse RDF, you have the loop in the beacon, regular antenna on the airplane. I actually don't know how used the system was in the US. From my reading online, I got the idea that it wasn't like incredibly common, but I'm not sure. Feel free to correct me on that one. But the technology sort of led into VOR, which is what we use more in the modern day, even though that's kind of going away too now. You'll see, when we talk about VOR, you'll see the references and how they're very similar. So the next iteration of navigation in the RDF family is called ADF or NDB. So ADF stands for automatic direction finding, and NDB stands for non-directional beacon. I've seen these before, and in my mind, they were kind of interchangeable. ADF, NDB, whatever. Some people call it this, some people call it that. They're not exactly interchangeable. So ADF, the automatic direction finder, is the component of the system that's in the airplane. It is the thing that's finding the direction, which is non-directional beacon, is the beacon that's on land. That's the transmitter. And non-directional means that it's just a normal antenna that broadcasts in all directions, right? It's not like the reverse RDF antenna, which does encode a direction in it in a way, right? Because you have the rotating thing, and every time it points north, it broadcasts something. So there's nothing of that. It's just simply a beacon that broadcasts. Maybe it broadcasts its identifier so that you can know who you're looking at. So it's actually the exact same as RDF, but more automated in how the bearing is calculated in the cockpit. It was given a different name, automatic direction finding instead of radio direction finding, because it allowed the pilot to automatically and continuously calculate their bearing to the beacon, rather than having to just take a reading when the pilot had a spare moment to like spin the antenna. This would just constantly do it for you. And the way it did it initially was the exact same principle as RDF. There'd be a tiny little like spinning antenna inside of a machine, inside of the box, that would just spin it for you and measure when there were nulls, and then display on the cockpit display the bearing to the beacon. Later on, that was replaced with just a set of antennas. And by measuring the time difference between all the little antennas inside the box and the phase difference, it was actually able to calculate where the signal must have been coming from, right? We can think about it like this in a simple case. Let's say you just have 3 little antennas sitting in the box, and we have an NDB that's broadcasting over here on the left. If it sends out its signal, the antenna on the left of the box will receive that signal ever so slightly before the 2 antennas that are further into the box, right? And by measuring those differences, you can compute where the signal must have come from. And this has the benefit in that it's solid state, right? There's no moving parts, less things to break. It's probably a little more accurate, and you can make smaller equipment. If any of you have flown with ADF in an airplane, this is probably what it was, this system. I've actually never flown with ADF, so I don't know. I would like to, though. And like I mentioned, there's a display in the cockpit, so instead of having to just look at the bearing based on where the antenna was, there's a little dial that has a little picture of your airplane in it, and then just an arrow that points in a direction that says, okay, with reference to your airplane, which is the one in the picture, that's the direction to the beacon. So it's simply just an arrow that points to the beacon. Very simple. So the only thing that you can measure directly with ADF is your bearing to the beacon. But if you're clever, you can actually also measure your distance to the beacon. So what you can do is, so you know which way to go to the beacon. You can turn your airplane so that the beacon is directly off one of the wingtips. And you'll know this because you'll look at the ADF and you'll see the arrow directly perpendicular to the picture of the airplane, meaning it's off to one of the sides. And then you can fly for some amount of time and at a set fixed speed. And then you can measure, okay, after I've flown at this speed for this amount of time, how far is the bearing changed? And then you can take the number of degrees changed, and there's a formula where you plug in your speed, how long you're flying, and the bearing changed, and it tells you your distance from the NDB. And that sounds a little bit magical, but let's actually think about how that works. If you're very close to the beacon, and we can see it, let's say it's right out the window, and you put your wing on the beacon and you fly for a minute, the beacon's going to be way behind you, right? It's going to it'll go from 90 degrees to almost 180. So there'll be a huge change in the bearing because you're so close. If you're very, very far from the beacon, hundreds of miles, maybe it can't reach that far, but very far, you can imagine if you fly for 1 minute with the beacon on your wing, it's still basically on your wing after that minute because it's so far away, right? And so we know that your distance has something to do with how much the bearing can change in a set time. And it turns out it is, and there's a formula where you can calculate your distance in that way. It's not ideal, and it makes you do math, but in a pinch, it could be a very nice tool. I alluded to this a little bit earlier, but one really cool thing about ADF is that you don't need to use an official NDB, an official non-directional beacon. You can use AM radio stations to navigate. And so you could listen to the AM station, and if you know where that station broadcasts from, you can navigate with it. It's not the most accurate thing because the NDBs, the official NDBs were made and placed in locations with not a lot of distortion or errors, whereas the AM radio stations were not. So you might have those errors, but it's a lot better than nothing. And I really just love that idea that you can navigate, if the FAA decides to stop supporting NDBs, which they are getting rid of them, then you can, this equipment doesn't become useless. You can just do it on the AM radio stations, which are still here, and there's lots of them. It's also very long range. It uses, similar to the AM radio frequencies, which can travel, probably hundreds of miles, depending on the conditions. And sometimes the signals can bounce off of the atmosphere, so you can get readings from very, very far away. So after ADF, the next evolution was VORs and DMEs. We'll talk about VORs first, DMEs second. Any of you that are pilots, I'm sure you've worked with VORs before. While the system is being phased out for GPS, and the same with ADF is, there still are a decent amount of active VORs. And at least when I did my instrument training, which was in 2020, I was required to learn how to do VOR approaches. VOR stands for VHF, omnidirectional ranging. Is that right? Omnidirectional range station. VHF, omnidirectional range station. Close enough. And it follows a principle very similar to reverse RDF, where you have kind of something rotating in the beacon and then something fixed, a fixed antenna in the aircraft. So there are two main parts of a VOR. There is a transmitter, an omnidirectional transmitter that transmits in all directions, and there is a rotating narrow transmitter By narrow, I mean that instead of in all directions, it only transmits in a narrow band right in front of it, right? So the only way you'll receive it is if it's directly looking at you. And the way I understand this now, I think this is true, that it is no longer a rotating antenna, but it uses something called a phased array, where you have like an antenna that can be like electrically modulated to point the beam in a specific direction a lot more accurately than like a little motor could spin an antenna. But the best way to think about it is, a rotating narrow beam and a broadcast beam that broadcasts everywhere. And from here, it works basically the same as reverse RDF. As the narrow beam rotates through north, the broadcaster will broadcast the identification for the station, and then the narrow beam will start sweeping. And then once you hear that narrow beam, you can measure the difference in time between receiving the identifier and the narrow beam. And using the known rotation speed of the VOR, you can calculate what radial you are on for the VOR. And since the VOR station is a little bit more complex, naturally we have a little bit more complex equipment in the aircraft. So you'll remember for the RDF, we just had an antenna that we would spin, and then we would just calculate based on how we rotated the antenna where the bearing was. For ADF, we had a little dial in the cockpit that actually pointed basically to the tower. For VORs, now we have a display where you set the desired radial that you would like to be on. So you see like a little picture of an airplane in the center, and then kind of a compass rose around it, kind of like a heading indicator. And then there's like a little thing you can twist that rotates that compass rose around the aircraft. And you rotate it until the desired radial is at the top. And then there's a white bar in the middle called the CDI, which stands for Course Deflection Indicator, I believe. And that tells you whether you are to the left or to the right of that desired radial. And then there's also a little to and a from flag, which tells you, are you going to the station or away from the station? That sounds complex. And it actually is a little bit complex. I remember being confused about VORs every now and then. Like I'd get caught up in something in the cockpit and like forget exactly what I was doing. But once you get used to it, it's kind of intuitive having that bar that swings left and right to tell you, oh, okay, if I want to be on this radial, I need to go a little bit to the left. If I want to be on this radial, I want to be a little bit to the right. And that's especially useful when you're like, when you're doing a VOR approach into an airport. It might say, okay, you're going to head towards this VOR on the, let's say, 165 radial. So you'll set the thing to 165, and then you'll just fly to keep the CDI centered, right? So if you see it deflecting off to the side, you know, okay, oops, I'm deviating from my course a little bit. I need to bring it back to center. And you just keep that thing centered, and you're guaranteed to bring yourself right into the airport. So that's kind of nice. So VFRs are very accurate. Out of all the systems we've talked about so far, VORs are definitely the most accurate. But the price you pay is that they are a lot shorter range than the other navigation methods we've talked about. They don't use the AM radio frequencies like ADF did, but the VHF frequencies, which generally require line of sight. There's some diagram I remember seeing it when I was studying for my PPL where it shows you like, okay, this is roughly how far you can see a VOR depending on your altitude and what type of VOR it is, but I don't remember how it was. But they don't work that far out. Like definitely within 200 miles, if I remember correctly, and generally closer to like less than 50. But like I said, it's more accurate. You can't, because you're not using normal towers, you have to use like the official VOR towers. You do have to rely on the government or airports or whoever maintaining these things and keeping them so that because they're shorter range, you have to make sure that you have two towers like relatively close together within the same range so that you can kind of jump from one to the next if you were traveling in IFR conditions using only VORs, right? You can't have like a long span without any VORs. So that is one downside, and we are kind of seeing that now as more and more VORs are being shut down and not maintained. There's kind of like gaps opening up between VORs where you have to navigate using another method, which generally isn't a problem. You just use GPS. But if GPS suddenly becomes not available one day due to GPS spoofing, then that could become a problem. So that's VOR. But if you remember from your pilot training, or if you've looked at a sectional map recently, you'll see that generally we don't see VORs alone. We either see something called a VORTAC or a VOR DME. And this is basically a VOR plus some other equipment attached. So let's talk about VORTAC first. So the TAC stands for TACAN, or TACAN. I think it's TACAN. It's TACAN, which I don't really know how this works. I didn't look into it because I've never used it because it's only for the military. But it's similar to a VOR. It provides you some sort of bearing information, but at I'm assuming, a more accurate scale because it's for the military. TACAN also provides you with a way to measure distance to the aircraft. So when you tune, in your civilian aircraft, if you tune to a VORTAC, you have access to the VOR portion of it, and you have access to the distance portion of the TACAN, but not to the bearing portion of it, because that's only for the military and your airplane won't be able to pick it up. So the VORTAC will provide you bearing plus distance to the beacon. VOR DME does the exact same thing. It's the VOR plus the civilian distance measuring equipment, which is what DME stands for. So how does DME work? So basically, a DME station is a transponder. So for me, the word transponder used to just mean the little box you have in your airplane that broadcasts out your squawk code. But a transponder technically is just a device that when it receives a certain signal, it automatically transmits a preset signal. So you can think of it as something that you send a message, it automatically replies, always. So the DME is a transponder, and the DME equipment you have in your aircraft is actually the initial transmitter. So when you're tuned into a DME, what your aircraft is doing is it's constantly sending a ping down to the DME station. The DME station receives the ping, holds it for a set amount of time, and then sends back a signal. And then on the aircraft, it is measuring the time between when you sent that ping and when you received back the signal. And using that, it can calculate the distance to the DME because it knows how long the DME held on to that before it broadcast, and it knows the speed of light. So you can calculate your distance. One thing you might notice though, is that distance is your slant distance. It is the straight line distance between the tower and the airplane. It doesn't take into account your altitude or anything. So for example, over the ground, if you're 10 miles out from the DME, but you're flying at, 20,000 feet, the distance is going to be longer than 10 miles. It's going to be the hypotenuse of whatever this triangle is, right? And so when you're far away from the DME and or at low altitudes, this isn't a big deal. But if you're at high altitude near the DME, then that measurement is not going to be very accurate of your ground distance, and you'll have to do a little bit of trigonometry to figure it out. But either way, it's a very cool system, very clever. And so if you have DME equipment in your aircraft and you're tuned to that VOR, you'll have your VOR indicator, your CDI, plus a little display. I've seen it on the nav radio before, where it's just a display of how many miles you are from the DME, 10.5, for example. A couple of times today, we've talked about instrument approaches. And like I mentioned before, an instrument approach is a procedure that you can follow that brings you into an airport, safely avoiding obstacles and making sure you're on a safe glide slope. And you can do all of this when you don't have visibility. as long as you have visibility of the runway by the time you hit some minimum altitude. Maybe it's 400 feet above the airport. All of the methods we've talked about so far are not great for doing an instrument approach exactly. They can bring you from far out into the area of the airport, but they won't be that useful for getting you down to the runway at a good glide slope. Like, there are VOR approaches, but they are non-precision, as they call it, and so they have higher minimum altitudes. But a lot of airports have something called an ILS system, which stands for Instrument Landing System. So I guess you wouldn't call it an ILS system, it's just an ILS, Instrument Landing System. This is a different type of beacon that's installed at near the end of the runway. I think it's about 1,000 feet into the runway, so near the 1,000 footers. And it broadcasts in a certain way that allows you to kind of follow the beam down to the runway. And these, up until I think they have precision GPS approaches now, but prior to that, this was the only way to do a precision approach to pretty close to the ground using radio navigation. And so the way this would work is there are two components. There is a localizer and there is a glide slope. So the localizer makes sure that you're lined up horizontally with the runway. Basically, make sure that you're not too far to the left or too far to the right of the runway. The way it does it is that there are two directional transmitters, meaning that they point in a certain direction. They're not broadcasting. One of them points a little bit to the left of the runway, and one of them points a little bit to the right of the runway. And they both broadcast on slightly different frequencies. And so when you're flying, if you're perfectly centered on the runway, you should be able to pick up a little bit of each signal. So the resulting signal should be a mixture of the two. Whereas if you're too far to the left, you'll hear the left signal a lot stronger than the right signal, and vice versa if you're too far to the right of the runway. And so you have equipment in your aircraft that can calculate how much of each signal it's hearing and display that result on a VOR style dial in your cockpit, which has like the CDI needle like we had before that will swing to the left and to the right, depending on if you are to the left or to the right of the center line of the runway. So it lines you up side by side. And then the glide slope is the same thing, but rotated 90 degrees. And that makes sure that you're not too high or too low from a nice stable approach. And I believe most ILSs are set up to bring you down at about a 3-degree glide slope, if I remember correctly. But the idea is the same, right? You have two different frequencies, and a frequency for like slightly above the glide slope and a different frequency for slightly below the glide slope. And depending on how much of one frequency you hear, your aircraft can calculate if you're a little too high or a little too low of the ideal glide slope. So when you're flying an ILS approach, basically what you're doing is you're just like keeping your eyes focused on that dial, making sure that CDI stays centered, and making sure that glide slope indicator is right in the center. It's not going up, it's not going down. Both pieces are directly in the center. So in my opinion, those are the main ways to do radio navigation. There's two more things I want to talk about. There are a lot of ways to do radio navigation. Like if you just look at the Wikipedia page for this, there are tons of topics in there that I didn't talk about. And not all of them are applicable to aviation, so I kind of stuck to the ones that are the most commonly seen in aviation. RDF they don't use anymore. I just talked about it because it was kind of like the first one used in aviation, and Amelia Earhart's airplane had it famously. Like if you see pictures of her aircraft, there's always that little loop on the top. But yeah, ADF, NDB, VOR, DME, ILS, these, even though they're being phased out, are still kind of common, at least in the United States. Like you'll see all of these things on the sectional. And if you're an instrument pilot, I'm sure you've done many ILSs. But yeah, the last two I want to talk about are slightly different like schemes than the ones we've talked about so far. And the first is just simply like radars and transponders. So one method of radio navigation is just radar, right? You have somebody like air traffic control who has a radar able to pick up your aircraft, and then they just tell you where you are over the radio. So the basic principle here is that the radar emits a signal at a frequency that will not pass through a solid object, but instead will be reflected back, right? Different frequencies of electromagnetic radiation can pass through different substances. This is like if you've ever had a satellite TV, like DirecTV, sometimes when it storms, you won't be able to get a signal. That's because whatever frequency that DirecTV is using, it is not able to go through clouds that have water in them, right? But some other services claim that they can go through clouds, like Starlink can go through clouds because they have access to another frequency that can go through clouds that have water in them, right? So radar is selected so that solid objects reflect the electromagnetic radiation back to the source. So when the radar sends out that pulse, it measures how long it takes for it to come back to the transmitter, and by just like kind of with the distance measuring equipment, by knowing the speed of light, you can calculate how far away the object is. And if you have a very precise radar, you can actually kind of see the shape of the object based on how far away each little point on the surface of it was from the transmitter. So if you've ever been in an air traffic control place, like air traffic control tower, I have not been, but I want to. They have a radar screen that has all of the aircraft in their airspace on it. And the transponder, which is in your aircraft, interacts with the radar system in a certain way to help out air traffic control. So when we were talking about the DME, we mentioned how DME is technically a transponder, which means that it receives a signal and then automatically replies. The transponder in your aircraft is the same way. So just a standard transponder, what it does is when it receives the radar signal, it emits a signal with your squawk code, the code that you typed into your transponder, which is 1200 if you're flying VFR. And I think it also encodes your tail number. And so that will show up on the radar screen of air traffic control. So they'll see all the little blips for the aircraft, plus the squawk codes and identification for the aircraft. If they have a transponder. If you don't have a transponder, then nothing shows up, obviously. You might, if you've ever done an instrument flight, you might have noticed that air traffic control will frequently ask you to ident after you first make communication with them, and then you push the little ident button on your transponder. And what that does is when the radar hits the transponder emits the signal with the information, but the signal has a special flag set that the radar on the ATC end picks up and makes that one flash. So from ATC's perspective, you push the ident button and then your aircraft lights up on their screen. So oh, okay, that's the guy I was just talking to. And it helps them pick out who is who. You might have heard about Mode C transponders, which are now in the US required to fly within the Mode C veil of certain airports, like Class Bravo, Class Charlie airports, which I think became a law in maybe 2021 that you had to have that. The Mode C transponders encode the pressure altitude of your aircraft, and they send that out when they emit their signal to air traffic control. And the reason for this is that radar is not good for measuring the altitude of the objects. It's just good for finding out how far they are out and in what direction. And so by sending back your pressure altitude, the ATC can have an idea of where you are in 3D space. Not only where you are in an aerial view of their area, but also how high you are above other aircraft, so they can space out the aircraft a little bit more efficiently. And then they have the Mode S transponders, which encode your I believe, your GPS altitude, not just your pressure altitude, plus like your speed and maybe your aircraft location. So it just gives ATC even more information about where you are and where you're going and how fast you're going. So that's that for radar. And then the last one I want to talk about is called LORAN, which you might have heard about. It's not really used anymore. In fact, I'm pretty sure it's been decommissioned basically completely in the United States. And it was more frequently used for boating, but I wanted to talk about it because it was used in aviation a little bit. And interestingly, the Cessna 170 that we bought last year came with a LORAN system. Obviously, we couldn't tune it to anything because there's no LORAN station still running anywhere near us. But it was kind of cool. Like, it worked. It would turn on, and I thought it was cool. We had to take it out because it broke eventually. So yeah, LORAN stands for long range navigation, and it works differently than all the methods we've talked about before. It uses something called hyperbolic. Is it hyperbolic navigation? I guess. It uses hyperbolas. So unlike the previous systems, it requires 2 ground stations to work. So basically how this works is, let's say you have 2 ground stations and they both broadcast a signal at the same time. Depending on where you are in relation to these towers, you will probably receive those 2 signals at a different time, and you can measure the difference in arrival time between those 2 signals. But you know the locations of the towers. So if you look at a map and you plot all of the positions on the map where your arrival times between the 2 towers differ by what you observed, that shape will plot a parabola, right? And so that parabola is your line of position. So we can talk about like the simplest case where that parabola degenerates into a single line. And that's the case where, let's say you received both signals at exactly the same time. So one possibility is that you are directly in between the 2 towers, right? Directly in the center. Or you could be off to the side, but equidistant between the towers, where the triangle formed by the towers and your aircraft makes an isosceles triangle, right? And if we plot all the possible points, that would form basically a line that like cuts the 2 towers in half, right? If you receive like a little bit of a difference between the 2, then that will form like a hyperbola just to one side of that line, either up or down, depending on which one you're closer to. And so you can just take my word for it that if you plot the possible positions for a given difference in time receiving the signals, you get a hyperbola. If you do this with another set of towers, you'll get a second hyperbola. And so if you plot these 2 hyperbolas on your map, you can look at their intersection points. And there could be up to 2 intersection points, if I remember correctly how this looks. But one of them is generally like far away and clearly known to not be correct. So you can narrow it down to 1 pretty easily. So yeah, that's LORAN. Pretty simple. One little just note, I did mention that the 2 towers would broadcast simultaneously. That is not how it works in practice, just because that would require both towers having incredibly accurate clocks that are completely in sync with each other. So instead, what they'll do is one tower will broadcast, and when the second tower receives the broadcast from the first, it will broadcast. And these 2 towers have a known distance between them, and therefore a known time of travel for the signal between the 2. And so anyways, you're still able to effectively calculate the difference in received signal on your end, and then still plot the hyperbolas, but it doesn't require having both towers synced to a very accurate clock. So yeah, I think that just about sums it up for radio navigation. Like I said, there was a lot of stuff I didn't cover, but those were the main ones. And then notably didn't cover GPS. We'll do that in the next episode. But yeah, If you have any questions or comments about radio navigation, definitely let me know. There's a lot of stuff I don't know, obviously. There's many things I'm not sure about, like physics and how exactly all this stuff works. And I would definitely love to learn more. But yeah, thanks for watching.
Thank you for listening to the Wing Wag. If you liked this episode, please consider subscribing. And if you're out flying today, make sure to give somebody a wing wag.